Okay, in this video I'm taking another look at the second order linear constant coefficient homogeneous recurrence relation. Here I'm saying that the leading coefficient is non-zero because if it were, then this term would be gone and you'd just be dealing with the first order. Those are much easier to solve. You can solve it using guessing. You can also generalize this up to higher orders, and in those cases you would still want to make the assumption that the leading coefficient is non-zero because if it weren't, you could just go down to the next order. So this is the recurrence relation I want to solve, and I can also write it in this other form. If I divide by a and I subtract these two terms over to the other side, then I get this. I introduced some new constants here, alpha and beta. Alpha is just negative b over a, beta is negative c over a, but it's the same thing. Okay, so what I saw in the last video, which I recommend you watch first, is that this was the solution to this type of equation, usually, except for a few exceptions. And so what I want to make my induction hypothesis is that f of n can be written in this form, and that's the key, that it can be written in this form. There's other ways, there are possibly other ways that it can be written. And so if you're wondering what these constants are, lambda 1, lambda 2, those just depend on what a, b, and c are, but they do not depend on the initial values of the sequence. C1 and C2, those are going to depend on a, b, and c, but they're also going to depend on f0 and f1. So if you're wondering why make this the induction hypothesis, and with all these specific things about lambda 1, lambda 2, C1, C2, check out the last video and you should be able to see why they are. It came from the fact lambda 1, lambda 2, those are the reciprocals of the roots of the denominator of the generating function, which depends on a, b, and c. And C1, C2, those had to do with the numerator of that equation, and those did end up depending also on f0 and f1. So to solve this thing, first we have to look at the base case, of course. And so if I look at the case P0, then that's just going to tell me that f0, this is equal to C1 plus C2, because here I have zeros, so those are just ones. And so the point here is I'm supposed to be able to say whether this is true or false. And so it seems like there's not much going on here. It's kind of hard to tell what's even going on. So this is saying if I choose an f0, then can I find a c1 and c2 where if you add them together you get that f0? So if I choose 7, I could have like 3 and 4, 2 and 5. So there's plenty of options here. Remember, C1 and C2, those do depend on these initial conditions. F0 is one of them, so that's going to be okay. The interesting thing here is that since this is a second order equation, if you look at this equation here, I need to know the previous two terms in order to figure out what the next one is. So in order to find the second term, I need to know it is the first and the 0th. So I'm going to have a second base case. And if you'll notice, I left an extra space here after the word case and before this colon so that I could put an S in there because there's two base cases. The next one is just going to be C1, lambda 1, C2, lambda 2. And so now the question is, if I choose an F0 and an F1, can I find C1 and C2 where this system is consistent? And, well, imagine if lambda 1 were equal to lambda 2. Then that would mean that F1 is equal to lambda times F0. And lambda does not care what F0 and F1 are. So after you chose your F0, you'd be stuck with whatever f1 was lambda times more than it. You wouldn't have a second choice there, so that wouldn't work. But in fact, I'm making the assumption here. I forgot to write this one down. There's a couple other things I want to assume here in my induction hypothesis. I want to say lambda 1 is not equal to lambda 2. They're distinct. And then I also want to say that lambda 1, neither of them can be 0, so they're distinct and non-zero. Okay, so if they're not equal, then the question is this thing consistent? And I'm going to leave that as an exercise, but it's not hard to do. Just slap this stuff into a matrix. I did it. If you do it on a napkin, you should get something that looks like this. For your C1 and C2, notice that they depend on F1, F0, lambda 2, lambda 1. Is this right? I don't know. I did it on a napkin, and napkins are unreliable. So anyway, if you go on to the induction step, then it's going to be a little different. I'm gonna do a strong induction here. So what I want to do is suppose that P of I is true. And what's I? This is just going to be a number ranging from 0 all the way up to k plus 1. So the difference here is from the other videos that I've had with induction are this one I'm assuming that all previous cases are true before I can prove the k plus 2th case, whereas in the other videos I was only assuming that the previous case was true. This is just going to make it a little easier. Really, you only need the previous 2 cases. If you're wondering why I stopped at k plus 1 here and not just k, that is just because it'll make it a little easier to do. It's really it doesn't matter. It's just a letter. So if I look at what is f of k plus 2, that's what I'm interested in now. Since all the statements are true up to the k plus 1th statement, I want to prove that the k plus 2 statement is true, because that would imply that they're all true since I have these base cases. 1 would imply the 2 would imply the 3. So if I look at this, I'm just going to plug it into this equation up here. So this is just going to be alpha times f of k plus 1. Over here I'm going to have beta and f of k. And so since the k plus 1th statement was true and the kth statement was true, I can replace this f of k plus 1 with what the statement says it is. This is just going to be c1 lambda 1 to the k plus 1. Over here this is going to be c2 lambda 2 to the k plus 1. And I can do the same with this other one over here, the fk. This is just going to be c1 lambda 1 to the k, c2 lambda 2 to the k. Okay, so this is starting to go off the screen here. Okay, so now what do I want to do? I want to rearrange these, and I want to rearrange them in terms of lambda 1 to the k and lambda 2 to the k. So I'm doing like an expand and refactor. So if I look at how many lambda 1 to the k's do I have, in this first part here I have alpha times c1 times lambda 1, and it looks like I'm going to have a c1 over here too, so I'll factor that out as well. So over here I have alpha lambda 1, and then over here I have beta. Both of these have c1 lambda 1 to the k. And I can do the same thing with the second one. This is really the hard part here, not messing up this. So I'm going to have alpha lambda 2 plus beta times c2 lambda 2 to the k. Okay, and so if you remember, my induction hypothesis was that f of n can be written in the form of c1 lambda 1 to the n plus c2 lambda 2 to the n. And lambda 1 and 2, those are dependent on a, b, and c, which equivalently they're dependent on alpha and beta. So down here, what if I just choose this part here? What if I just say that's lambda 1 squared? What if I just say this part here, that's lambda 2 squared? It seems kind of ridiculous to say something like that, but remember, all I'm trying to prove is that fk plus 2 can be written in the form of c1 lambda 1 to the k plus 2. And so that would be exactly what I would get. I would get c1 lambda 1 to the k plus 2. Here I would get c2 lambda 2 to the k plus 2. So yeah, you could pick like, you could say this thing here, that's equal to lambda 1 cubed or something. Then your lambda 1 would be different than mine, and it would also get you nowhere because you're trying to prove that it can be written in this form. So it is a little arbitrary and it's kind of strange. But anyway, so this is the k plus 2 statement right here. So what we find is that the k plus 2 statement is true given that all statements up through the k plus 1 are true, and so that implies that the statement is true, p of n, this statement is true for all n. But I don't know how much time, this video is going really long again. I want to look at what these assumptions over here tell me, because something kind of cool comes out of this. This one over here, this is saying lambda 1 squared is equal to this stuff. This is saying lambda 2 squared is equal to this stuff. Notice that these two expressions look exactly the same except for the subscripts. This one's 1, 1, this one's 2, 2. But they're both alpha, lambda, beta. So what I can write in both cases is, let's see, is this on the screen? Yeah. Okay, alpha times lambda 1 plus beta is equal to lambda squared. Oh, whoops, I forgot that's what I was just talking about. I don't want to put the subscripts here. This is true for lambda 1 and for lambda 2. And so what I can do is here, I can replace the alpha and the beta with what they really are in terms of the a, b, and c. So let's see, that was up here. Alpha, that was just negative b over a. Beta, that was negative c over a. So let's see, here, I'm back on screen. Okay, so this is negative b over a lambda plus, or well, it's going to be minus c over a is equal to lambda squared. Multiply both sides by a, add these terms to both sides, and what you get is a lambda squared plus b lambda plus c is equal to 0. And so lambda is equal to minus b plus or minus square root of b squared minus 4ac over 2a. Okay, so this is kind of cool because it tells you actually what lambda is going through this process. Notice that I said lambda 1 is not equal to lambda 2. That must mean that lambda 1 is one of these roots and lambda 2 is the other one. Also, since they're not 0, that means that this thing, the discriminant, b squared minus 4ac, must not be 0. And so what that means is that this technique, or this solution, with these assumptions, this is only valid if the discriminant, the b squared minus 4ac from this equation, is not 0. And then we already talked about why a can't be 0, or why you wouldn't even want to consider that. So one last thing I want to mention, this equation here, if you just take this fn plus 2, you replace it with lambda squared, you take this fn plus 1, replace it with a lambda, take the fn, replace it with 1, that'll get you straight to this equation. And this is called the characteristic equation. And then the values for lambda, the lambda 1, lambda 2. For the next several videos, I will refer to those as the roots of the characteristic equation. There's a single word for it, roots of the characteristic equation. That's 5 words. There is a single word for it, but I'm going to leave it as a surprise because you probably already know the word and it probably already means something to you, but I'm going to instead show you that it is the same thing and then start calling it by that thing instead.